Hi, class. In this section, in this lecture, I want to move into section 3.2, which is called comparing the infinite, like how you compare two sets that have infinite number of elements. And this is about pairing up collections via a one-to-one correspondence. Okay, so I briefly talked about what a one-to-one correspondence was in section 3.1, so we're going to continue on with that. All right, so here's some questions for the lecture. How much bigger is the set of rational numbers? So rational numbers are any number that can be expressed as a fraction in the set of natural numbers. And then how many fractions are there between the numbers 0 and 1? Well, when you think about the rational numbers, how many numbers can be expressed as a fraction? Well, there's an infinite number, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, so on, so on, 2/5. 3/5, 4/5, 5/5, 6/5, 7/5, all those things are rational numbers. So it seems like there's a ton of them. There's an infinite number. But then what about the natural numbers? Well, the natural numbers is the set of 1, 2, 3, 4, 5, and so on and so on. Well, how much bigger is the set of rational numbers, the set of natural numbers? Well, it quote unquote seems like there's more rational numbers, but there's an infinite number of rational numbers and there's an infinite number of natural numbers. So believe it or not, they're exactly the same. All right, how many fractions then are there between the numbers 0 and 1? Think about it. 1 over 2, 1 over 3, 1 over 4, 1 over 5, so on, so on. 2 over 3, 2 over 4, 2 over 5, and so on, and so on, and so on. So there's actually an infinite number, okay, which you might not have believed. All right, so remember talking about the cardinality. So the cardinality is the number of things in a set, okay, the number of objects in there. So two sets have the same cardinality if there's a one-to-one correspondence between the elements of one set and the elements of the other set. So like, for example, the element of the set of the stars on the flag with the set of the number of states, well, there's a one-to-one corresponding because one star can get mapped to each state and each state can get mapped to one star. So that works out. Okay, so think about this. All right, and this is kind of getting towards this concept of mapping with one-to-one. So if you have the natural numbers, okay, so the set of the natural numbers, 1, 2, 3, 4, 5, 6, and so on and so on. If you compare the cardinality of the natural numbers with the natural number 1 deleted. So if we have another set, okay, so we call one set n, which is the natural numbers, 1, 2, 3, 4, 5, 6, so on. And then we have another set, we'll just call this m, which is 2, 3, 4, 5, 6, 7, and so on. What is the cardinality of this? Okay, so it might seem like right off the bat that, oh, set n must be bigger, okay, because, it has one more element. That's actually not the case. Remember, they both go to infinity. So how can you compare this and see that they both go to infinity? We'll take the number 1, map it to 2. Take the number 2, map it to 3, 3 to 4, 4 to 5, 5 to 6, 6 maps to 7, and so on and so on. You could form a one-to-one correspondence that would just go on forever and ever and ever. So which set is larger? Well, neither. They're both the same. They're both an infinite set. Okay. So neither one is larger. Okay. You can see this otherwise. If you compare the cardinality of the even natural numbers with the cardinality of just the natural numbers, again, they're the same. 1 gets mapped to 2, 2 to 4, 3 to 6, 4 to 8, 5 to 10, and so on and so on and so on. And they would keep going on and on forever because there's an infinite number of even natural numbers. There's an infinite number of natural numbers. The cardinality is the same. They're the same exact size. So, just think about, is there a set of numbers that has a greater cardinality than the cardinality of your natural numbers? Is there a set that has a cardinality greater than infinity? No, there isn't. Okay. Same with the integers. All right, the integers are like -2, -3, -4, -5, so on, all the way to 0, 1, 2, 3, 4. Do the integers and the natural numbers have the same cardinality? Absolutely. They're both infinite sets. So even though it might seem like there are more integers than natural numbers, Not the case. The cardinality is the same. They both have an infinite number. So you can see kind of the mapping here, how you would do this, and we'll do some examples of this, okay, so you can see, explain the correspondence. So the natural numbers, if you take 1, map it to 0, take 2, map it to 1, take 3 to -1, 4 to 2, 5 to -2. All right, if you look at the even numbers, 2, 4, 6, okay, the even numbers, so whatever number it is, where n is the natural number, 2 times the natural number gets mapped to the integer n. And then the odd numbers, 1, 3, 5. So like the first odd number, this n would be 0. So 2 times 0 plus 1 is 1, gets mapped to -n, so which would be -0, which is 0. The next one, 2 times 1 plus 1 is 3. 3 gets mapped to negative. You can see it. Okay, so you can form this correspondence mapping, and they have the same cardinality. All right, this was a little weird, so let me try a different example, and you can see this. Okay, so let's have two sets. Okay, let E stand for the set of all natural numbers, or even natural numbers, so it's the set 2, 4, 6, 8, so on, and O stand for the set of odd natural numbers, so O is 1, 3, 5, 7. Show that sets E and O have the same cardinality by describing an explicit one-to-one correspondence between the two sets. All right, I'm going to load this up in Excel here so you can kind of see, so I can write the numbers easily. Okay, so here are the even numbers, 2, 4, 6, 8, 10. And here are the odd numbers, 1, 3, 5, 7, 9. Okay. So this is going to be the n notation for the even numbers and that n notation for the odd numbers. Okay. Well, the first element in this set, so element 1 is 2. Well, that's 2 times n. The second element is 4. Well, so 2 times 2 gets me 4. Yes. The third element is 6. Well, 2 times n, which is 3 for the third element, is 6, and so on. 2 times the fourth element, so 2 times 4 is 8. And again, the fifth element, 2 times 5 is 10. Or 2 times 5 is 10, excuse me. So the same thing here with the odd numbers, okay? How do you get 1 from the first element? All right, it's you might think to do n, but then element number 2 is equal to 3. Okay, so if you just had n is equal to 2, it would be 2. It doesn't work. So the odds are always going to be expressed as 2n minus 1. So element 1, 2 times 1 minus 1 is 1. Element 2 should be 3. Well, 2 times 3 is 4. Minus 1 gets me 3. And this will always work for the n, for the odds. So the one-to-one correspondence, any element number, okay, which would be 2n, corresponds to the corresponding element over here, 2n minus 1. So there is a one-to-one correspondence from E being 2n to O being 2n minus 1. So you can do it that way. All right, let's try this one. Okay, this next one here. Let the set, we'll call it EIF, be the set of all natural numbers ending in 5. Okay, so that set is 5, 15, 25, 35, and so on. Okay, describe a one-to-one correspondence between the natural numbers and the set EIF. All right, so let me just do this, and the same thing in Excel with this E notation for you. Okay, so we're going to have the set of natural numbers and the set EIF. All right, so the natural numbers we know are the numbers 1, 2, 3, 4, 5, 6. And EIF here was 5, 15, 25, 35, 45, and 55. Okay. Well, look at this. This is 5 times 1, 5 times 3, 5 times 5, 5 times 7, and so on. So it looks like we want to map these numbers to an odd multiple over here. So remember, we're going to take the notation n for the natural number of this set. So element 1 is this. Element 2 is this. Element 3 is this. Element 4 is this. So on and so on. Well, remember, element 1 is going to be 5 times 1. Well, let's see if that's 2n times 1. Okay? Well, when n is 1, yes, this becomes 2n times 1, okay, which is 2 times 1 minus 1, which is 1. And then what we're going to do is we're going to take that number and multiply it by 5. All right, so let's see when n is equal to 2 if we get 15. 2 times 2 is 4, minus 1 is 3, times 5 is 15. Nice. See if the same thing here. 2 times 3 is 6, minus 1 is 5, times 5, yes, gets me 25. So this correspondence works. So there is a 1-to-1 correspondence, all right, between the set n, okay, and this is letting n represent the element in set n here, to the set EIF, letting 5 times 2n minus 1 represent the elements in set EIF. All right, I know this can seem a little weird and confusing, but I hope these examples helped, and the textbook does a fantastic job also walking you through this. Thanks, class.